Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to describe matrices. In this topic, we will define matrices and the dimensions of a matrix. We will describe the rows and columns of a matrix and the corresponding column vectors. We will explain how to identify specific entries within a matrix. We will describe the zero matrix, and we will define the diagonal, superdiagonal, and subdiagonal entries of a given matrix. Alright, we have now seen that these two problems are equivalent. Given this system of linear equations, we can write this as a linear combination of vectors equaling a target vector. The vector b is simply the right-hand sides of the equations, and each column or each vector are the coefficients of one of the variables. We will now define a matrix A that amalgamates the coefficients of the unknowns. So, given this system of m linear equations in n unknowns, we will define the following matrix that simply contains a grid of the corresponding coefficients. And whereas in the system of linear equations, if one of the coefficients is 0, we may leave that value out. In the matrix, we will explicitly place a 0 in the appropriate location. For example, given this system of 3 equations and 3 unknowns, here the matrix A stores those coefficients, and as you can see, the second equation has a 0 coefficient for x3, but nevertheless we enter that value into the matrix. Here we see a system of 2 linear equations in 4 unknowns, and here is the corresponding matrix of the left-hand coefficients. Finally, here's a system of 5 linear equations in 2 unknowns, and here is the corresponding matrix of the left-hand side coefficients. The dimensions of a matrix corresponding to a system of m linear equations in n unknowns is said to be m by n. So, alphabetical ordering. A matrix is said to have m rows and n columns going across. Individual entries of a matrix may be identified uniquely by a pair of indices. Here we see the matrix capital A. We will always represent matrices as uppercase, italicized Latin letters. The entries of a matrix capital A will always be lowercase italicized a's with an appropriate subscript. So the entry A sub ij indicates that that entry is in row I and column j. So for example, in this matrix here, the entry 2, 3 appears in row 2 and it is in column 3. For example, here we see a 7 by 6 matrix capital C, or we'll just refer to it now as C. So for example, the entry here, 8.2, is at index 3, 2, being in the third row, second column. Here's my personal aide-memoir for remembering the location of the entry Cij in a particular matrix. The phrase is down the stairs and into the crypt. So, given the entry Cij, we go down to row I, and then across or into the matrix to column J. Now, because a system of linear equations is equivalent to finding a linear combination of vectors equaling a target vector, we will need to, in some cases, identify specifically the column vectors of a particular matrix. So here we have the matrix A with each of its entries. It is an m by n matrix, m rows, n columns. We may represent this as a sequence of n vectors where each vector is assumed to be m-dimensional. And of course, we will wrap it in parentheses. So in this case, the first vector A1 represents the first column of the matrix, and so on and so forth up until the vector A sub n is the last column of the matrix. And as before, the columns of matrices A, B, and C, all uppercase and italicized, are bold-faced A Roman sub J, bold-faced and Roman J, B sub J, and bold-faced Roman C sub J, respectively. Again, recall that the entries of these matrices are A sub ij, B sub ij, C sub ij, each lowercase and italicized. So for example, given this particular matrix here, the column vectors are A sub 1, which is the entry is 3, 5, 2, A sub 2, and finally A sub 3 being -1, 0, 8. Now, when the dimensions of the matrix M and N are equal, for obvious reasons, we will call such a matrix a square matrix. So for example, here the matrix A is a 2 by 2 square matrix, B is a 3 by 3 square matrix, and C is a 5 by 5 square matrix. Now, very often we are going to have to refer to specific entries in a general matrix. One of these are the diagonal entries of the matrix. These are the entries of the matrix where the indices are equal. So this is a 7 by 6 matrix and therefore has 6 diagonal entries. Those entries are C11, C22, C33, 44, 55, and the last one C66. In formulas, we will often be referring to the diagonal entries simply by having the same index. So for example, CII. All entries of a matrix that are not on the diagonal are called off-diagonal entries. All entries immediately to the right and above the diagonal are said to be on the superdiagonal, while all entries to the left or below the diagonal are said to be on the subdiagonal. Now, in a square matrix, it's much easier to identify the diagonal entries which go from one corner to the other, and subsequently the superdiagonal and subdiagonal entries. Like the zero vector, the m by n matrix of all zeros is described as the m by n zero matrix. It is denoted by an italicized O subscripted with m and n. Following this topic, you now understand the definition of a matrix. You know the dimensions of a matrix are the number of rows by the number of columns of that matrix. If these are equal, we will say that it is a square matrix. You know that where to find, for example, the entry A sub 5, 7 in a particular given matrix. you know which are the diagonal, superdiagonal, and subdiagonal entries of a given matrix, and you understand the idea of the zero matrix, specifically the representation of the m by n zero matrix. Here are the references, acknowledgments, the colophon, and a disclaimer. Cheers!